Imagine a world of shapes, a world beyond our everyday experience. This is the world of topology, where donuts are no different from coffee cups, where surfaces bend and twist but never break. It's a world explored by brilliant minds like Henri Poincaré, a French mathematician who lived over a century ago. Poincaré wasn't just any mathematician, he was a visionary, a pioneer in exploring the very fabric of our universe. Poincaré was particularly interested in spheres, those perfectly round objects we know from our own planet. But he wasn't thinking about ordinary spheres like the Earth. He was imagining a sphere in 3 dimensions, a concept difficult to visualize, but crucial to understanding the shape of the universe itself. This 3-sphere, as it is called, became the heart of a mystery that would captivate mathematicians for a century. Poincaré believed that this 3-sphere was special, unique in its way. He proposed that any shape resembling our familiar 3-dimensional space, but finite in size and with every loop on it shrinkable to a point, could only be a 3-sphere. This simple yet profound statement became known as the Poincaré conjecture, a puzzle that would challenge some of the greatest mathematical minds of our time. Picture, if you will, a world confined to the surface of a sphere. This sphere, our entire universe, is finite, limited. You could travel in any direction and eventually end up back where you started. Now try to imagine that same concept, but instead of a 2-dimensional surface, we have 3 dimensions. This is the essence of the 3-sphere, a concept that stretches our imagination. The 3-sphere is a closed space, like our hypothetical spherical world. There are no edges, no boundaries, and yet it is not infinite. It's as if you could travel in any direction, through any dimension, and eventually loop back to your starting point. This idea, while baffling at first, is crucial to understanding the very fabric of our universe. The Poincaré conjecture, at its core, asks a simple question about this strange 3-sphere. If a space looks like our familiar 3-dimensional world but is finite and has this peculiar looping property, can we be sure it is indeed a 3-sphere? It's like trying to identify a mysterious object hidden in a box by feeling its surface. We can explore its contours, its bumps and dips, but without seeing it directly, can we be certain of its true nature? Imagine tying a loop of string around an apple. You can easily slide that loop off the apple without cutting the string or breaking the fruit. This simple act illustrates a key concept in topology, the idea of a loop being contractible to a point. Now imagine trying to do the same thing on the surface of a donut. A loop threaded through the hole can't be shrunk down to a point without cutting the donut itself. This difference in loop behavior is a fundamental distinction between a sphere and a donut, at least in the eyes of a topologist. Poincaré's conjecture revolves around this idea of loops and their behavior. He claimed that in any space resembling our own, if every imaginable loop could be shrunk down to a point without encountering any obstacles, that space, no matter how distorted, must be a 3-sphere in disguise. It's like saying that if you can always slide a loop of string off a mysterious object, that object, regardless of its apparent shape, must be an apple. This conjecture, seemingly simple on the surface, proved incredibly difficult to prove. For decades after Poincaré posed his question, mathematicians were left grappling with the challenge of how to pin down the elusive 3-sphere, how to definitively prove that any space with these looping properties couldn't be anything else. The search for a solution became a mathematical odyssey, leading researchers down unexpected paths and pushing the boundaries of geometric thinking. Imagine a world where shapes can morph and change like molten glass, smoothing out their bumps and wrinkles over time. This is the world of Ricci flow, a powerful mathematical tool that would eventually unlock the secrets of Poincaré's conjecture. Enter Richard Hamilton, an American mathematician who dared to tackle this shape-shifting world. Hamilton's insight was to treat the curvature of a space, its bumps and dips, like heat flowing across a surface. Just as heat spreads from warmer areas to cooler ones, smoothing out temperature differences, Ricci flow could smooth out the geometric wrinkles of a space, revealing its underlying shape. Imagine a crumpled piece of paper slowly ironing itself out, its wrinkles disappearing until its true flat form is revealed. That's the essence of Ricci flow. Hamilton made significant progress using Ricci flow to tackle the Poincaré conjecture. He showed that in many cases Ricci flow could indeed transform a crumpled, complicated space into a smoother, more recognizable form. However, he encountered formidable obstacles, regions where the flow became uncontrollable, like singularities in physics where the known laws break down. These roadblocks, these mathematical black holes, prevented him from reaching a complete solution.